Okay, we're going to briefly talk about fully analyzing chemical equations. So in this chemical equation, you can see that magnesium is added to hydrogen chloride, which yields magnesium chloride plus hydrogen gas. So there are two reactants, right? Your magnesium and your hydrogen chloride. And there are two products, and they all have a relationship to each other. If you were given the number of moles of any of these substances used, you can use it to figure out the number of moles of any other substances in this equation. So if you had 1 mole of magnesium, it would be equal to 2 moles of hydrogen chloride, right? There's a 1 essentially there and a 2. 1 mole of magnesium would be equivalent to 1 mole of magnesium chloride, and likewise 1 mole of magnesium would be equivalent to 1 mole of hydrogen. Let's say there were less than 2 moles of hydrogen chloride. If there, in this equation, if there were less than 2 moles of hydrogen chloride, there would be leftover magnesium when the reaction was complete. This would be your limiting reactant if that were the case. If there were more than 2 moles of hydrogen chloride, all the magnesium would be used up for this reaction, but there would be leftover hydrogen chloride. So your magnesium would be the limiting reactant. I hope you can see that from talking about limiting reactants previously. And hopefully you can also see how a balanced chemical equation can show you which reactant is limiting, right? Let's move on from here. All right, we're briefly going to talk about relating products to reactants in chemical equations. So basically, you can now figure out the amount of a reactant needed in order to make a specific amount of product. And so in this example, what they're saying is that they want you to make 2 moles of FeCl3, right up here. They want you to make 2 moles. So if you know that you are making 2 moles, your product, and they want to know how many moles of each of the reactants are necessary to do this. Well, this particular problem is fairly easy because in your reaction it makes 2 moles, and that's what you need. So in order for this reaction to occur in making 2 moles, you're going to need 2 moles of FeTiO3. You're going to need 4 moles of HCl, and you're going to need 1 mole of Cl2. I hope that's obvious to you. Let's keep going. I am not going to work through all of the examples in your book. I feel like your book does a pretty good job of doing that, and I feel like it would be extra redundant. But if there is a specific problem that you're having trouble with, please let me know, and I'm happy to go over it with you. But the basic idea at this point is that, you know, they want you to see stoichiometry is a great method of using balanced chemical equations to determine how much material you're either producing or starting with when you're given a specific amount of one of the substances in a chemical equation. Okay, and then stoichiometric coefficients, they help us convert the number of moles of one substance to moles of another substance, again within the same balanced equation. And this is going to take us into Gay-Lussac's law. Basically, Gay-Lussac, Joseph Louis Gay-Lussac was a French chemist who identified stoichiometric coefficients and related them to the volumes of gases of substances in a chemical equation. So Gay-Lussac's law says the stoichiometric coefficients in a chemical equation relate the volume of gases in the equation as well as the number of moles of substances in the equation. You will need to know this, so make sure that you know it. Now, it does have a limiting factor. It can only be used in stoichiometry if the substances being compared in the problem are gases. Okay, so it only works for gases. So that's something to know. And in this particular example right there, using Gay-Lussac's law, you can see that 3 liters of hydrogen gas reacts with 1 liter of nitrogen gas to produce 2 liters of ammonium gas. Okay, so we can use the liter when we're talking about volumes of gases. And in this problem, those are gases, and so they can be related in this way. All right, so getting over into the mass relationships and chemical equations. So chemists really don't measure material in moles, right? Usually it's measured in mass, oftentimes grams. So you need to be able to use stoichiometry so you can relate the masses of substances within the chemical equation, right? So in this example, right here, if you can use stoichiometry to relate the number of moles of each of the substances to each other right here, right? But right here, they're saying, what if we asked you to make 50 grams? So what would you do? Well, we're not given number of moles, right? But can you convert grams to moles? Because that's what we're given. Yes, you can. Hopefully you remember doing this from the previous module. So that is something that you can do. Okay. All right. I do want to talk about one of the examples in our book. Okay. So we are told a chemist needs, this is example 8.6. A chemist needs to produce 100.0 grams of GlCl3 using the following reaction. We have 2 gallium plus 6 hydrogen chloride, and it will yield 2 GaCl3 plus 3H2. And it asks you how many grams of gallium and hydrogen chloride are necessary to accomplish this. Okay, so we're given 100 grams of gallium chloride of Cl3, GaCl3, and we need to find grams of reactants. So what is going to be your strategy? What is going to be the way that you tackle this problem? Well, the first thing you're going to do is you're going to convert your 100.0 grams of GlCl3 to moles of GlCl3. Okay? Then, after that, you're going to figure out how many moles of the reactants you need. Okay? And then after that, you're going to convert the mole amounts to grams. And that's going to be your strategy. Okay? So first convert your grams right here to moles. 100.0 grams of GlCl3. And then right here, 176.2 grams equals 1 mole. Okay, well, how did they get that? How did they get 1 mole of GlCl3? Remember your periodic table? Okay, so right here, Ga is 69.7 AMU, and then you're going to add 35.5 times 3 for your chloride. Okay, and that's going to give you 162.2 AMU. Well, we know that 176.2 grams of GlCl3 will equal 1 mole of it, right? This is from the previous module. So you got to remember this. So then you're going to convert and you're going to get your moles. Now, what was the strategy after that? Well, you figure out how many moles of your reactants you needed, right? And you can look up here and see that. So 2 moles of gallium yields 2 moles of GlCl3, and 6 moles yields 2, right? They're getting it from these numbers right here. And it talked about it at the beginning of this module. Okay, so then you're going to take your 0.5675 moles of GaCl3 and convert. So 2 moles of it equals 2 moles of gallium, and that will give you the moles of gallium you need. And then using it the same way with 6 will give you the number of moles of hydrogen chloride. Okay? So then you take that and you convert these mole amounts to grams. Now remember, you're going to need your periodic table to do this again. So gallium, we said it earlier, but it's right here, right? It's 69.7. So you're going to take your moles of gallium. 1 mole is 69.7, and that's going to give you the number, sorry, my hand was in the way. That's going to give you the number of grams you need. Same thing with hydrogen chloride. Your hydrogen is 1.01 AMU, and then the chloride is 35.5, so you get 36.5 AMU, which means 1 mole of it will equal 36.5 grams, and then you just convert to your gram amounts. Okay, so hopefully you can see how it's important to have a strategy when you tackle these problems, and you can go back and forth. If you don't understand this, please let me know. You are going to need to know this for your test. Okay, I just briefly wanted to discuss figure 8.1, which is talking about mass relationships in chemical equations. So basically, if you are given grams, you can convert that to moles. Then you can make the mole relationship to other substances in the equation into moles. Then you can convert those back to grams. What you cannot do is go grams to grams, which is what they're trying to say here. But you can convert grams to moles, make a mole relationship, and convert back to grams. Okay, that's going to be important, so I just wanted to highlight that. Okay, let's do this one. In the following reaction, Mg solid plus 2H2O liquid yields MgOH2 solid plus H2 gas. What mass of Mg must you use to make 2.8 times 10 to the 4th grams MgOH2? Okay, so you are given a product in grams, and you need to know what mass in grams of a reactant. So remember what you do. You take your grams, you convert to moles, you make your mole to mole relationship, and then you convert to grams. So that's what we're going to do. All right, so the first thing we do is we use a periodic table to get the mass, and Mg right here, it's 24.3 AMU, plus, remember this subscript means there's 2 oxygens and 2 hydrogens. So plus 2 times 16 plus 2 times 1.01 equals 58.3 AMUs, which means 1 mole of MgOH2 is equal to 58.3 grams, okay? So we take our given amount, what we started with, 2.8 times 10 to the 4th grams, and then we multiply by what we figured out. 58.3 grams per mole tells us how many moles, 480 moles of MgOH2. Then we're going to make our mole-to-mole relationship. So in 1 mole, it's a 1-to-1 relationship. So right here, you have 1 mole for MgOH2 is 1 mole Mg. So it gives us 480 moles. And then we just need to convert to grams. So you know from the periodic table just a moment ago, I told you that Mg is 24.3 AMUs, which means 1 mole is 24.3 grams. Sorry, sometimes I say the wrong number. And so you make your conversion. 480 moles of Mg, 1 mole of Mg is 24.3 grams, which equals 12,000 grams. Okay? So I went a little bit fast on that, but hopefully it makes sense. It's just another example. Okay, let's look at example 8.8. A chemist decomposes an unknown compound. The products of this decomposition are 12.00 grams of carbon, 4.04 grams of hydrogen. What's the chemical formula of the unknown compound? So we need to set this up and solve to figure out what the unknown compound is. All right, so we know it's a decomposition reaction, and we know that it yields carbon and hydrogen. So our compound's going to have some number of carbon and some number of hydrogen in it. And then it's going to yield carbon plus H2. Why H2? Hydrogen is a homonuclear diatomic, okay? So then we're gonna set it up and solve. So the mass of carbon, we know from the periodic table, is 12.0 AMU. So we know that 1 mole of carbon is 12.0 grams of carbon. So if we have 12.00 grams of carbon, that's what they told us right here, and we do our conversion, 12.0 grams of carbon, 1 mole, they cancel out and it gives us 1.00 moles of carbon. Okay, so right here in front of this carbon is going to be a 1. Now let's solve for hydrogen. So we go over here, the mass of hydrogen, we have 2, so it's going to be 2 times 1.01 AMU equal 2.02 AMU. So it means 1 mole of hydrogen equal 2.02 grams of hydrogen. It told us right here that it yielded 4.04 grams of hydrogen. So 4.04 grams of hydrogen times 1 mole over 2.02 grams hydrogen, they cancel out, it gives us 2.00 moles of hydrogen. So right here in the equation, we are going to have a 2 for hydrogen, a 1 for carbon, a 2 for hydrogen. So what does this mean to have a balanced equation? There's 4 hydrogen and 1 carbon. That means our unknown compound is going to be C1 or just C, H4. That is the unknown compound for this problem. All right, so it gets a little bit more complicated than the example that we just worked out. We said that the mystery compound was CH4, but in reality, it could have been C2H8. It could also have been C3H12. There are different examples it could have been as long as the carbon and hydrogen remained in the 1-to-4 ratio. There could be several accurate possibilities of unknown substances. Okay, so we're going to get into molecular formulas and empirical formulas. So a molecular formula is a chemical formula that provides the number of each type of atom in the molecule. Whereas the empirical formula is a chemical formula that provides a simple whole number ratio for the atoms in a molecule. So in our example that we just did a second ago, our empirical formula was CH4. The molecular formula could have been CH4, it could have been C2H8, it could have been C3H12, etc. Okay, right here in example 8.9, it gives you 3 A, B, and C. The molecular formula of 3 compounds are listed below. Determine the empirical formula. Remember, we just said the empirical formula, this is the simplest whole number ratio for the atoms within a molecule. So right here for A, C4H12, both 4 and 12 are divisible by 4. So the simplest formula is going to be CH3. You divide 4 by 4, which gives 1, and 12 by 4, which gives 3. All right, for this one, the empirical formula for Na2S2O8. Everything's divisible by 2. So that's going to give NaSO4. Hopefully you see that. And the last one, K2Cr2O7. Nothing is divisible, so this is the empirical formula. This is the simplest formula. All right. Okay, just 2 more things that I want to point out as well. As an example 8.10, you will see this. But if you have the empirical formula for a compound and can find a molecule's mass, you can calculate the molecular formula. Okay, and that's what this problem does. So make sure you look through and understand what it's doing. And also the definition of molar mass. The mass of 1 mole of a given compound is the molar mass. Okay guys, that's all I have for this video. For your test, make sure you understand what a stoichiometric coefficient is and you can define it. Make sure you understand what a limiting reactant is. Make sure you understand the definitions and the differences between molecular and empirical formulas. Make sure that if you are given an empirical formula and a molecular mass, you can convert it to its molecular formula. I just talked about that very briefly. Work through your example problems. There's several different problems throughout. I don't think any of them are super hard. Make sure you're familiar and can state Gay-Lussac's law. Those are all the hints I have for you. You can use a periodic table on your test as well as a calculator. Let me know if you have any questions. Good luck. I'll see you all on Monday.